And before the next speaker, I do have a small announcement. Oh, what's happening? Yes. This talk is actually has actually received a Best Paper Award by junior researchers. Congratulations. And I should also mention that this comes with a check.
Oh,
so that should also be mentioned for the talk in the last session, which also won a similar prize. So they also get this check. So congratulations. And now let us move to your talk.
Thanks a lot, Cynthia. So my name is Petar Vukmirović, and today I will be talking about a procedure for efficiently solving the full unification problem. So
you need to share the screen again. I overrode it.
Okay, let's see. Can you see this? Is it okay now?
Yes, now it's okay. Thank you.
Okay, thank you. So let's see what I mean by procedure for efficiently solving the unification problem. Well, first of all, we are interested in the unification problem, which is the problem of finding a substitution that makes two terms syntactically equal for some notion of equality. And then further, we are interested in higher order unification, in particular unification between two simply typed lambda terms, modulo alpha, beta, eta equivalence. And as we all know, this is an undecidable problem, and moreover, it is non-unitary, which means that even though there might be a unifier for the problem, there is no guarantee that there is a most general unifier, which is why we introduce the concept of a complete set of unifiers, which is roughly a set of unifiers such that any other unifier is obtained as an element of this set. Now, one of the hardest issues in higher order unification are so-called flex-flex pairs. Those are the unification constraints where both left and right-hand side have free variables as the head terms. And traditionally, there are two ways to deal with them. We can either ignore them or postpone them, or enumerate a complete set of unifiers for them. The first problem is called preunification, and the second one is called full unification. We have decided to deal with full unification because of recent advancements in automatic theorem proving, which actually require you to enumerate complete set of unifiers for all problems. And because we are using such a procedure in efficient theorem provers, we needed to be efficient on two levels. Theoretically, we need to provably create less redundant unifiers than current state of the art. And practically, we should collect all kinds of optimizations available either in the literature or undocumented implementations and actually build them in the procedure. So we base our work on Jensen-Petrzykovsky procedure or JP procedure, which is state-of-the-art in full unification theorem proving for the last 50 years. And this procedure works as follows. It identifies positions in terms where they disagree, and then it chooses one of those disagreement pairs, so-called, and then based on the disagreement pair and also all the free variables occurring above it, it is going to decide which substitutions to apply to solve this disagreement pair. And then because it needs to enumerate a complete set of unifiers, it is going to build a search tree in which all of those substitutions are explored in turn. But this is a little bit misleading because actually this tree can have infinite branching. There might be infinitely many substitutions that are applicable at a given position. On the other hand, for preunification, a state-of-the-art is so-called Huet's preunification procedure, and it has architecture that is more similar to that of first-order algorithms. And it is because it doesn't solve a problem for a pair of terms. Actually, it solves a problem for a list of constraints, but it also destructively transforms the problem, which means that if it sees that that heads of the current unification problem are rigid, which means either constant or a bound variable, it is going to decompose them. And it is going to do similar to next chosen pair. And when it chooses the next pair, it is going to postpone because this is pre-unification procedure. And then we get to a flex rigid pair. Now, Huet's procedure again computes some bindings that it needs to apply to solve the flex rigid pair. And it builds a tree similarly to JP procedure. But what's very nice is that this procedure is always finitely branching. When we set to design our full unification procedure, we were inspired by those two procedures, but we have set some clear goals ahead of us. We needed a procedure that is going to be less redundant than what we have observed previously. It needs to terminate more often than those procedures, and it also needs to be efficient enough to be implemented in high performance tools. And one of the first decisions that we made on this goal was to set with a architecture that is reminiscent of for example, Huet's procedure. So we solve a list of constraints and we destructively transform the problem. So let's see how that looks on this example. So we are going to destruct like Huet. Then this first pair is easily solved. And now we get to something which Huet doesn't have to do. We need to solve flex-flex pairs. And the way we do this is heavily inspired by JP algorithms. So we modify some of the bindings that are applied in JP algorithm. And we also modify the way the bindings are applied. So the first thing that is a huge difference between our and JP procedure is the JP procedure, as I said before, when it chooses this disagreement pair, it has a choice of applying a substitution either above the disagreement pair or at the position of disagreement. But not only that, it has the choice to, it can actually interleave those two processes. So it can apply the substitution at the position of disagreement and then above, and then at the position of disagreement again. We have actually proved that without loss of completeness in our procedure, it is enough to either decompose and continue, which means I see that those two variables are the same. And then I say, well, I will ignore them and then now try and solve this disagreement. Or I apply all possible bindings that I can at this position of those variables and only then continue. This has some advantages that we are going to, look with some examples. So if we are solving this example here, our procedure will do two things. As I said before, it can either choose to decompose and then get into this smaller problem, and then apply projection, which is the only thing that can solve this problem, or it can decide to apply a binding at the head and solve the problem in this way. JP procedure, on the other hand, is going to get to those two unifiers in relatively similar way to ours, but because it has this interleaving, it might choose to apply a substitution at the disagreement pair, which is this subterm here, and then decide to apply, for example, projection, which will not lead to a solution, and then apply something that is actually going to solve the problem to get a unifier. However, this unifier is clearly redundant with respect to the one that we found before. One obvious problem that JP procedure also has is that it retraverses common context every time it needs to discover the disagreement pair. And it is this can be a huge problem in deep terms that can arrive in high-order theorem proving. Our procedure destructively decomposes the problem and never has to retraverse the common context over and over again. Now, in high-order theorem proving, but I suppose also in some other techniques, it can be the case that a free variable occurs in its own arguments quite often. And we need to deal with this case very efficiently, which means that when a procedure decides to apply a substitution, we will get this huge term with a lot of beta read access. And if you remember, JP procedure, to actually decide which next step to take, it needs to get the position of the disagreement pair well, it needs to get all of them to actually choose which one it's going to work on. But even worse, it actually needs to look at all the positions above. This means that JP procedure must fully normalize terms, which can take quite a lot of time, as you know. Our procedure, on the other hand, it makes decisions only based on the head symbols, which means that we don't need to apply the substitution and beta normalize aggressively. We need to do that only until the heads of the term are known, or in other words, until we get the terms in head normal form, which allows us to actually find clashes lazily and more efficiently than other procedures. Then another problem with JP procedure is that it is more redundant than Huet's procedure on flex rigid pairs. If we take this previous example, we see that JP procedure applies some very simple substitutions, namely projection and imitation, which are very tame, which are very simple. On the other hand, JP procedure, for this pair, it is going to apply so-called iteration binding for flex rigid pairs, which has this shape. It is this huge term in which details of which I will not go into. But if we abstract away a little bit from this term, we can see that for each length n, we need to create this tuple of bound variables, and also for each variable iterate over all possible types. So it is a horrible infinite branching rule. We have shown that without loss of completeness in our procedure, iteration is not necessary for flex rigid pairs. And this means that we are graceful with respect to Huet's procedure. Another thing is that iteration is not only applicable at flex rigid pairs, it is also applicable at flex pairs. And if we go back to the example where we showed the redundancy of JP procedure, the situation is even worse, even on the simple example, because JP procedure doesn't even terminate on this example because of application of iteration. Our procedure does terminate with only those two unifiers, because we proved that iteration is not necessary if we have same head flex pair that has no functional arguments. We actually proved something a bit stronger, but for this case, this suffices. Now, what might come as a surprise for people coming from first order unification is that JP algorithm is not going to terminate for some simple example, such as x equals f of x, which is first order. And to solve this problem, we thought that we are definitely not the first ones to actually encounter this. So we went to literature and found that there is a huge body of work on algorithms that enumerate complete set of unifiers for some fragments of higher order unification, and we call such algorithms oracles. And we have found some interesting oracles. So, for example, Huet described this fixpoint oracle, which solves the problem of naked variable, so non-applied variable, equals some other term which has some constraints. Then pattern fragment, which is a very well-known fragment, very well behaved, that actually is just which has the simple constraint of any free variable can be applied to only distinct bound variables. And we have functions as constructors, which has more complicated fragment test, but it properly subsumes pattern unification. We have integrated oracles in our procedure very tightly, which means that as soon as we get a disagreement pair, we will ask the oracle, what do you know about this disagreement pair? And oracle can give us three answers. It can give us an answer, this is in my fragment, and I have found the complete set of unifiers. It can tell us this is not in my fragment, but I know that there are no solutions for this. Or it can tell us this is not in my fragment, I don't know anything about this pair. In first two cases, we are happy because we either use the elements of CSU to continue on, or we prune this part of the search tree. In the third case, we actually need to continue solving like we didn't call the oracle at all. It turns out that oracle were extremely useful because they help us achieve all of our main goals. They usually return smaller CSUs than general purpose procedures. They are decision procedures, which means that they will be able to tell us if something is not unifiable. And they can usually be implemented much more efficiently than general purpose procedures such as ours. we have actually also discovered one new fragment which admits an oracle, and it is based on the concept of solid terms. We say that a term is solid if its free variables are applied to bound variables, which can be repeating, or it is applied to ground base type terms. Ground base type terms, here I mean ground is without free variables, and base type means of not functional type. And let's see some examples. So the first term is not solid because it has this free variable argument. The second one is not solid because it has a function argument. And the third one is solid. And what's very interesting is to see that we actually allow terms of arbitrary order to be arguments, as long as function is not directly the argument of a free variable. And we have then proved that this problem, S equals T, S constraint T, has a finite CSU for which we provide an algorithm to enumerate this CSU. If one of the terms is linear, which means that there are no repeated free variables, they share no free variables, and terms are solid. Let's see an example of this. An example of this is this flex-flex pair. And what is very interesting is that for solid problems, flex-flex pairs actually have the most general unifier. So any flex-flex pair that is solid is going to have a most general unifier. And this is actually a huge improvement because, for example, on this problem, both JP and our algorithm will not even terminate because iteration is applicable for them. So this actually can be quite helpful in some cases. And also, if we are solving the matching problem, this condition here disappears because one of the terms is not going to have free variables in the matching problem. So it is more permissive if we are solving the matching problem, which also happens quite often in the practice. So we have implemented our procedure in Zipperposition theorem prover, which is higher order superposition theorem prover, and we have implemented fixed point pattern and solid oracles. And before we started our work, there was an implementation of JP procedure by Alexander, one of my co-authors, that actually was extended to check if the terms are first check if the terms are in the first order fragment, and if so, then run the first order algorithm. So it was a little bit improved JP procedure than the one available in literature. And so we compared our procedure with this baseline, and we tested on 2,606 monomorphic TPTP problems. So those are sometimes relatively higher order problems that might need complicated unifiers. And we tested on 832 sledgehammer generated problems, which are mostly first order with some higher order axioms inside. We gave a 60-second CPU time limit for each run of the prover. So let's see the results on TPTP. So JP procedure. So our procedure with no oracles outperformed the JP procedure significantly. And this is the conjecture mainly due to the design of procedure and actually removing a lot of redundancy. So this laziness that is in our procedure is actually quite helpful on some hard problems, but also the design itself, which has this no retraversal and in general more efficient design, actually helps improve over JP even if you implement no oracles. But it is a very good idea to implement at least fixed point oracle and pattern oracle as well, because this improves quite a bit. Then on sledgehammer problems, the effect is much less dramatic, which is expected because these are mostly first order problems, and it is not expected that unification is a big factor here. And so we are only barely better than JP procedure if we have no oracles, and we are somewhat, well, we are reasonably better if we include fixpoint and pattern oracle. So in summary, we have designed a new complete unification procedure that is less redundant, terminates more often, and outperforms state-of-the-art procedures. Future work is mostly concerned with creating new heuristics, because right now pretty much everything is more or less carved in stone. So we have decided on some choices that we thought were good, and there is no choice there right now. So we plan to design some new heuristics. There are also some alleys that we can explore when it comes to better termination behavior, and we also plan to implement this in competing theorem provers such as E. Yeah. So thank you for your attention. And if you like the illustrations that I used, I would suggest you to visit FreePic and Andro and support the artists that create those beautiful pictures. Thank you for your attention.
And thank you, Peter. Stefan had a remark. Stefan?
Yes, I was just wanted to point out that Zipperposition is currently running in the CASC competition, and it looks like it's going to win with exactly, I guess, these algorithms that Peter just told us about. It's nearly unbeatable in the lead.
Well, thank you for updating me on that. I couldn't check it myself. It would be disrespectful. But yeah, so one of the biggest jumps that we saw actually in previous version of Zipperposition, which implemented a weaker, incomplete version of this algorithm, was due to unification. So, and also in the paper, we actually describe how we implement higher order indexing data structures, which are still in their infancy. And if I'm not mistaken, Zipperposition is one of the only theorem provers that has powerful indexing data structures for higher order terms. So, I mean, but also in your experience, it is also that theorem proving heuristics are actually very important, and this is also something that we have been working on. So I cannot conclusively say which is the greatest factor, but this can definitely be achieved. So there is also one more question in Q&A window. Shall I answer this one?
Yes, unless Gopalan wants to add anything.
Yeah, no, thanks for the nice talk. The question is it's straightforward. I was wondering if you could still stick with head normalization while you're thinking of using oracles. They might interfere with each other.
Yeah, this is a great question, and we in the paper actually this is described. So oracles need to be implemented in such a way that they also head normalize. So there are two ways, as you have noticed. You can either fully normalize before calling the oracle, which is inefficient. What we have done is we have actually changed the oracles to obtain terms that are only in head normal form, and then inside the algorithm also work with that. And what is nice is that almost all the algorithms that are available in the literature that we are aware of can be very easily massaged so that they use a head normal form.
Does that answer your question, Gopalan?
Yeah, no, I'm aware of that. It's just that in the main procedure, you can't avoid having to deal with full normalization if you're using oracles, I think. I think we've got these kinds of problems eventually in the context of Lambda Prolog and also systems like Abela and so on. But I think you're describing the same thing. I should look into how your enumeration helps, which seems to be a very good idea. Yeah.
So I don't know if maybe I was unclear. So I was actually saying that we can change the oracles so that they work with 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 head normal forms, because, for example, a pattern unification also makes all decisions based on the heads, and to discover whether a term is a fragment or not, we only do this check when a certain operation, which is tied to this fragment, needs to be performed. So, for example, when we have a free variable in the pattern fragment, only then do we normalize its arguments to actually see their distinct bound variables.
Right, right. No, I agree with that. I mean, I don't see a problem with that. Yeah.
Okay, thanks.
Okay. So we have 2 more questions. I propose Michael goes first.
Okay. No. Michael asked, are there any higher order unification problems that older JP procedure solves and our procedure does not? So the last time I checked, and this was months ago, all the problems that were solved by our procedure were a superset by the ones that JP solves. Okay. And then there is another question by Luigi. What about adding this feature to script languages? I'm not sure I really understand this question. What do you mean by adding this feature to script languages?
I mean, add to imperative languages some logical feature, and in this case, you can use your procedure. I don't know if.
I don't know what in which exact part of the imperative language would you add higher order unification?
For example, imagine in Python you can add some unification feature and very simple basic unification feature. And at that point you could imagine very simple and efficient procedure like the one you have explained in this paper.
Yeah. That is very well possible. We have been looking at this only from the perspective of higher order tier improving. We have been working with this higher order tier improver, which actually needed full unification, and this is more or less the only angle from which we looked at this. But thank you for giving a tip.
It was just an idea to find other potential usage, because I think it's a very good tool. It's a very good. Very nice paper, so it would be nice also to find other applications.
Thanks a lot. Yeah, this is I think a good tip. It could be good to look in that direction.
Okay. Are there any further questions? If not, then thank you again, Petar.